Hello warriors, this is Miss Lemons, and today we are going to be going over heating curves, what they look like, and just the concepts behind them. It's also going to be an opportunity for us to color code and label the heating curve that is on our notes. Now, if you weren't able to print off those notes, don't worry. You can always freehand your heating curve. Just make sure you label it with the numbers that I have on mine, and feel free to pause the video at any time so that you can get all of the information down on your heating curve. So before we get into labeling our heating curves, let's just take a look at what this graph is showing us. I want you to notice the X and Y axes. Along our X axis, we have heat supplied, and we know that heat energy is measured in joules or kilojoules. Now for a heating curve, it's going to be in joules. The temperature is along the Y axis, and that's measured in degrees Celsius. Now look at the trend line. We have the trend line here, and you can see generally that as heat the temperature. So that means that it's a direct proportion. So as temperature increases, so does heat / kinetic energy. And that's a trend that we've known even since really the gas laws unit. So I also want you to notice that this heat curve has two leveled off plateaus or tables here, like these leveled off sections where there is no increase in temperature. Temperature remains the same, but you can see that the heat supplied increases. So the temperature stays the same during this phase change, which is what these plateaus are. I also want you to note that all heat curves will have two plateaus. One will be for boiling and condensation point, and the other one will be for melting and freezing point every single time. Okay, so I do want to point out these little plateaus. This will always be the melting or freezing point, right? If we're going from left to right, if we're increasing the temperature, we're increasing the amount of heat supplied, we are going to be melting, right? Going from solid to liquid. If we're decreasing the amount of heat, we're going to be going from liquid to solid, so freezing. Up here, the second plateau, we have boiling or condensation. So if we're increasing the amount of heat supplied, we're going to be going from liquid to gas or boiling. If we decrease the amount of heat supplied, we're going to be going from gas to liquid or condensing. Okay, so I have my own little key off to the left-hand side here. We're going to go ahead and draw the heat curve for water. Make sure you label your heat curve for water just so you know what the heck you're looking at. And remember that all heat curves are going to look slightly different, but they will all have two plateaus. You can use the same color coding system as me if you would like. You do not have to. I prefer color coding just because it keeps my thoughts organized, and I know that this is going to be a tool that I will continue to use for all of my calculations later on. So the first thing I want to point out is you'll notice that I have these boxes up above. Now my text is a little too large to fit everything in those boxes. If you can fit all of your information in those boxes, great. But you'll notice that each segment of the graph has been partitioned. So we've really chunked this graph into 1, 2, 3, 4, 5 chunks. So the first part I want to pay attention to are these two plateaus that I pointed out in the previous slides. This is where phase changes occur. So going from solid to liquid, liquid to gas, or the opposite direction. So as far as the matter, on our far left-hand side, anything that lines up on this line or falls on this line before that first plateau is going to be a solid. That means as we're going through melting, so if we're moving from left to right, we're adding more heat into the system, and so we're becoming more liquidy. Think of a melting ice cube. When we're going through melting, both solid and liquid exist at the same time. A melting ice cube, you'll see a puddle of water and the ice cube sitting on top of it, right? So water and solid are existing at the same time. As you move closer to the right-hand side of the screen or of this partitioned area, we'll have more liquid. Less liquid over to the left-hand side, right? Because we're just starting the melting process. So as we add more heat, we're slowly melting. There's more liquid being formed, less solid. And then eventually when we get to the very bottom of this first increase, we're finally 100% liquid. Then we're going to continue to increase the temperature and the heat supplied. We'll the second phase change will be existing as both liquid and a gas. And think about when you're boiling water. You're going to have water in the pot, and you're also going to have steam forming up above. So you have liquid and gas existing at the same time. Add even a little bit more heat, and then we'll end up with 100% gas. So anywhere that we have a phase change, we don't have a change in temperature, but for our these sections, you can see that we have an increase in temperature or a decrease in temperature if you're going the opposite direction. So there is a temperature change for these three sections. Also remember that the two plateaus are designated as your melting and freezing point, as well as your boiling and condensing points. For water, you can see that our melting and freezing point is at 0 degrees, and our boiling and condensing point is at 100 degrees Celsius. Okay, so in the previous video, we talked about the different enthalpy labels for all of our phase changes. We have the molar heat of fusion, which is for melting, the molar heat of solidification, which is for freezing, the molar heat of vaporization, which is for boiling, and the molar heat of condensation, which is for condensation. So what's really going to be important is our ability to place these symbols on our heating curve graph so we can use them for calculations later on. Let's go ahead and show where those are located. So here's where we're currently at with our labels. We're going to go ahead and place each of our enthalpies. So we know that each of those enthalpies are the enthalpy for phase changes. So those enthalpies are going to go in these green sections, not in the temperature changes, just the phase changes. So enthalpy for melting, the molar heat of fusion, that's going from solid to liquid. And then we're going, again, left to right. We're increasing the energy, molar heat of vaporization, going from liquid to gas. Now, if we were decreasing the amount of energy, we would go from gas to liquid, or you'll notice that I did liquid to gas here with the arrow just reversed, because technically liquid's over on the left and gas is over on the right. Whatever works best for you. And then if we decrease that temperature and heat energy even more, we're going to end up freezing that liquid into a solid. So notice again that the direction of the arrow is the only thing that I changed here. I did not flip-flop liquid to solid because we are actually technically moving on this graph right to left. Okay, so let's talk about the enthalpy of phase changes. Now, we can measure the heat content, or the enthalpy, delta H, of substances going through phase changes using the heating curve and two formulas. One of them you've seen before, Q equals MCAT. Specific heat of a substance, the change in temperature of a substance, and the mass of that substance gives us the heat content. And remember, delta H is equal to Q in this class. The new one that we're going to be learning about today is Q equals mole delta H of the phase change. And we can use this for when we don't have a temperature change. So we can place those equations on our graph so that we know when to use which equation in our calculations. So for all of our temperature changes, we're going to want to use Q equals MCAT because we have an actual change of temperature, a delta T. We wouldn't be able to use delta T or Q equals MCAT in the phase changes because phase changes do not have a change in temperature. You can see that by looking at this plateau. Notice that as we increase heat supplied, that the temperature stays exactly the same. So it's impossible for us to use Q equals MCAT. The other equation is going to be used instead for our phase changes. So that's Q equals moles of substance times delta H phase change, or the molar heat of the phase change. Okay, so how do we classify delta H, enthalpy, and Q, the heat energy during a phase change? Remember that delta H is equal to Q, but delta H is measured in kilojoules per mole, and Q is measured in joules, typically. Warning, we will have to convert using dimensional analysis to get the units to match. So we can't have kilojoules for one and joules for the other. Everything needs to be joules or everything needs to be kilojoules. So you will be doing a bit of converting for these problems. Before we get into calculations, though, it's kind of interesting and helpful to know that the heat absorbed by melting a solid is equal to the heat lost when a liquid solidifies. Think about this picture here. Melting is the opposite of freezing, right? And so it would make sense that because of the law of conservation of energy, that in order to melt a certain mole amount of substance, you need a certain amount of energy being put into the system. Endothermic reaction, we're putting energy into the system. And then in order to freeze the same amount of substance, you would have to remove the same amount of energy, right? In order to melt or to freeze the same amount of substance. So we've got endothermic, we're going to add 3 moles of energy or 3 joules of energy to this sample. And if we want to freeze the same sample, we would have to remove 3 joules of energy. So that's why it makes sense that the delta H of fusion, or the molar heat of fusion, is equal to and opposite the molar heat of solidification. And that's because of the law of conservation of energy. Likewise, if we're talking about vaporization and condensation, those also are opposite phase changes. So as we increase our heat energy, the system is going to have heat energy enter the system. So let's say we endothermically have 3 joules of energy added to the system in order to vaporize a certain amount of substance. If we wanted to condense that same amount of substance, we would then have to remove 3 joules of energy. So again, we kind of have this cycle here of adding in energy to evaporate, removing the same amount of energy to condense. And again, that's because of the law of conservation of energy. Energy can't be created or destroyed, it's only transferred, and it has to be equal to and opposite.